So continue our discussion of quantifiers. Let's take a look at disproofs. And disproofs really require us to understand the negation of the existential and universal quantifiers, because what we do to disprove each of those quantifiers is quite different. So let's take a look at disproofs. So in order to disprove the statement P, what we actually do is show that its negation, not P, is a true statement. So if that statement has a universal quantifier, well, since when we negate for all x, we get there exists x, well, all we need to do to disprove the original statement is to show that there exists one value of x, at least one value of x, that makes P false. The not P is a true statement. So our disproof can just be a counter example. We just need one example that works because the negation of for all is there exists. On the other hand, when we look at an existential quantifier, when we negate that existential quantifier, we get a for all, and we have to work a lot harder because in order to show that this new negation is true, we have to show that it's true for every single value of x. Okay? So we definitely have to work harder because we have to show that not P is true for all x. And we can't just use a counterexample. Counterexamples do not prove existential quantifiers. So let's do some examples. So for every n, 2 to the n minus 1 or 2 to the n plus 1 is prime. So scratch work. If we play around with this for a little bit, we realize this is actually wrong and it sort of smells false. To see why, let's just plug in a few numbers of few of the first values of n. So when n equals 1, we get 1 and 3. 3 is prime. N is 2, we get 3 and 5, both prime. N is 3, 7 and 9, 7's prime. 4, we get 15 and 17, 17's prime. 5, 31 and 33, 31's prime. But when we get to n equals 6, we get 63 and 65. 63 is divisible by 7, and 65 is divisible by 5, so neither of them are prime. So we've found a value of n for which this is false, and that's enough. So when n equals 6, so our proof can just say pick n equals 6. Well, since neither 63 nor 65 are prime, the statement is false, because we've found a value of n that makes it false. And our counterexample that we've just done there in that proof is really proving the statement there exists n so that neither of these numbers are prime, which is just the negation of this original statement. Okay? So when we negate for all, we just get that there exists. So in order to disprove a for all, we just need an example that makes it false. Okay. Let's do another one. For all a, b, and c, if A divides BC, then A divides C, or A divides B. And if we think about this, again, it smells false. It's sort of something doesn't feel right here. Well, since this is again a universal quantifier, it's for all A, B, and C, well, a counterexample is going to be sufficient. And if we think about it very carefully and we form the negation, which we should as part of our scratch work, what we're really producing here is there exists A, B, and C so that the hypothesis is true and the conclusion is false. So it's very important we understand how to negate an implication. Okay? So we just now need to find, because it's there exists, we just need to find an example of A, B, and C that do this. And if we think about this a little bit and sort of something about prime factors seems to be about the right thing to do here, and we can very quickly come up with an example. We can pick A equals 4 and B and C are 2. Well, then A divides 2 times 2, but A doesn't divide 2, A doesn't divide C. So here's our counterexample. So our proof, you can say proof, the statement is false, so we're telling the reader up front what's going on. Here's A, here's B and C. Well then, A does divide B, C, because 4 divides 4, but A doesn't divide B and A doesn't divide C. So we're just explaining to the reader what's going on here. Okay, so that's not bad. Well, let's look at the existential quantifier, and this tends to be a bit harder, okay? So, but sometimes we can be lucky, and instead of having to do an infinite number of things, we can actually reduce the problem down to some finite number of cases. So let's look at this example here. There exist prime numbers so that P minus Q is 999. Well, if we start thinking about odd and even, we can leverage the fact that if we have an odd number minus an odd number, we get an even number. So that suggests that one of these two numbers has to be even. And there's only one even prime number, namely 2. So it pays for us to think about what happens when Q is 2 or Q is any other prime. And that should be our scratch work. Well, when Q is 2, then P would have to be 1001. And we can check fairly quickly with a bit of computer algebra or a calculator, or even by hand if we're adventurous, that 1001 is 7 times 11 times 13, and so 1001 is not prime. And so when Q is 2, the only possible prime that it could be would be 1001, but that's not prime. On the other hand, if Q is not 2, it has to be an odd number, but that would make P an even number, and so it wouldn't be prime. So no such primes exist. So let's write this up. Okay, so this is a false statement, and we're going to split it into two cases. Q is either even or odd. Well, if Q is even, then Q had better be 2. It's the only even prime. Well, then P would have to be 999. So, no, P would have to be 999 more than Q, which is 1001, which is divisible by 7, so not a prime. So the only prime number it could be isn't actually a prime number. So there's case 1 done. On the other hand, if Q is odd, then we better have Q is 2k plus 1 for some integer k. But that makes P 2k plus 100, which is divisible by 2, and so not prime. And so in either case, there's no prime numbers that are going to work. So no such primes exist. Okay, let's stop there.